Let's now extend our discussion about the first law of thermodynamics towards open systems, in which there is mass that crosses the system boundaries. And so let's discuss the system that I have drawn here, where we have some sort of, tank that has an impeller in it with liquid stirring. And on the left side of the tank, we have some fluid entering in with a mass flow rate 1, a temperature 1, and a pressure 1. It goes in the tank, it gets mixed around, and then it exits the tank on the right-hand side with some mass flow rate 2, temperature 2, and pressure 2. And the temperature of the outlet stream is a little bit higher than the temperature of the inlet stream. But in order for the fluids to flow, the pressure on the inlet stream has to be higher than the pressure on the outlet, okay, in order for it to flow. And so here we've sort of talked about at least properties that one can measure, so some sort of physical properties. But another physical property that we also need to consider is the energy of the streams that are going into the system, out of the system, and also what the energy of the fluid within the system boundaries are as well. So energy 1, energy 2. And when we discuss our system, what we're going to be discussing is everything inside these blue lines. Okay? So that's going to be our system. To analyze this system, we should first start with a material balance. So with a material balance, we know that accumulation is equal to input minus output plus generation minus consumption. There's no reaction going on in our system. So that means this G minus C term is going to be equal to 0. Alright, at that point, we do know we have an inlet to our system. We do know there's an outlet. And in general, we do know that there may be some sort of accumulation going on in the system, depending on whether the inlet is greater than, less than, or equal to the outlet. Outlet. Okay? Alright, and so when we talk about accumulation, we could write it in terms of the derivative of the mass with respect to time. For the inlet into the system, that's going to be that m1 dot, and the outlet is going to be m2 dot. Therefore, from our material balance, we know that the dm dt is going to be equal to m1 minus m2. Okay? And so that's what the material balance simplifies down to for our system. But generally, if you're dealing with a system with many more flow streams, you could write your material balance as dm dt is equal to the summation from I1 equals 1 to however many streams there are, n. That's going to be equal to the summation of what I call alpha I, and then the mass flow rate, m sub I dot. And this alpha here, all this is a constant that determines the sign of the mass flow rate. And so if you're dealing with some sort of inlet stream, alpha is just going to be equal to positive 1. And if you're dealing with an outlet stream, alpha is going to be negative 1. And so this is consistent with our sign convention. If things are going into the system, they're positive. If they're leaving the system, they're negative. Alright, and so that was the material balance. Now that we have that in tow, we can move on to the energy balance. And since we saw from the material balance we're dealing with, a dm dt, or we're dealing with the mass balance on a sort of rate form, what we could do with the energy balance is we could start with our rate form. So let's use the rate form of the energy balance. And so in that rate form of the energy balance, we have dE dt is equal to Q dot plus W dot, right? And so that's what we had before. But now what we need to consider is the inlet and the outlet of the energies, or the energies of the inlet and outlet streams, okay? And so in our energy balance, we now need to add on a new term, which sort of looks like the material balance equation, but multiplied by that mass flow rate, we now need to add on some sort of specific energy term as well. Okay? As we know, energy can be split up into three contributions: the internal energy, the kinetic energy, and the potential energy. And so we could do the same thing here. Right. Where this lowercase u, that's what I'm using for velocity. Alright, and then I'll call this c sub I. Alright, and so just to emphasize, this is internal energy, this is the kinetic energy, and this is your potential. Alright, so that all three of those contributions make up the energy. Alright, so we have a form of the energy balance for the open system, but we could also play a few more tricks in order to simplify this equation down to make it easier to manipulate. Right? And so what we're going to do is we're going to remember that our work rate, our W dot here, that could be described as a sum of the shaft work plus the flow work. Right? If we look back at our system, with our fluids flowing in, they're being mixed, so that's why there's a shaft work term there. And they're also being pushed by the pressure, right? And so that's why we'll also need to consider the flow work of the system as well. And so our total work, our total W dot is shaft work plus flow work. And if we remember from the previous videos, we could also rewrite the flow work as this. Where it's equal to some mass alpha times some mass flow rate, and then times pressure times VI hat. Okay? Alright, and so we could take this identity and plug it into W dot in our previous equation. So what we have now is dE dt. It's going to be equal to Q dot plus shaft work only, and then plus a summation term. Is alpha I mi. It's going to be ui plus the pi vi that we got from the flow work term, this specifically that, and then plus changes in kinetic energy and changes in potential energy as well. Okay. Now if we look closely, what we end up having here is a ui plus a pi vi, and that is basically just our definition of enthalpy. So we could rewrite our energy balance in terms of enthalpy now on the right hand side. So that way we don't need to independently consider what the pressure or the specific volume of the streams are at the inlet and the outlet. So what we end up getting is now this equation with enthalpy built into it. Okay, so box this in. So what we have here is the energy balance for open systems. And so whenever you're dealing with an open system problem in this course, this is the energy balance that you should start with. Alright, one last thing I'll point out is if we're at steady state, that would mean that our dE dt is going to be equal to 0. Or otherwise, the energy within the system boundary lines, that energy is not changing.